All right, so this lesson is about something called an angle bisector. So you want to draw an angle, and this angle that I've drawn here, I'm going to make it 60 degrees. It's angle ABC, and we're going to start off by adding an angle bisector to it. So that's just something that goes through the vertex and divides it into two equal angles. So I've added this angle bisector through here, and you know that the angle bisector makes this angle and this angle congruent to each other. So these are both 30 degrees. Now if I put a point on this angle bisector, let's say I put a point right out here somewhere. So here's point P. Now I can name these angles. I have angle CBP right here is 30 degrees and angle PBA also 30 degrees. That's not too exciting, you already know that. But what you may not know is if I measure the distance from point P that's on the angle bisector to the sides of the angle. And when I say measure the distance, I don't mean just measure it from here to here. I mean measure it perpendicularly like this. And right here we have a nice right angle. So I'm going to measure also from P over here to BA, still perpendicular. So I have a nice right angle. And what you'll notice while I'm doing this, these measurements are popping up over here. And the distance from P to D is 4.71 centimeters, and the distance from P to E is also 4.71 centimeters. No matter where my point is on this angle bisector, you see those distances to the sides of the angle stay the same. Okay, so it's pretty basic. If you have a point on the angle bisector of an angle, then that point is equidistant to the two sides of the angle. And what I just said to you there is a theorem that you need to know. So we're going to write down the theorem real quick. The theorem is called the angle bisector theorem. I'll write it here. Angle bisector theorem. And all it says is just like I said, if a point is on the angle bisector of an angle, then that point is equidistant from the sides of that angle, or of the angle. So it's not too exciting. It just says if I have an angle and then I bisect and I put a point on it, no matter where I put that point on it, even put it way out here where you can't even see it anymore, it's always going to be an equal distance from that point to the sides of the angle. So what you remember is when there's an angle bisector, the perpendicular distance to the sides are equal. There's also a converse of this theorem. So there's a converse. I'm not going to write it down here. You can go ahead and write it down, and it says exactly what this says, except if a point is on an angle bisector of an angle, becomes the then part. So our theorem would now say if a point is equidistant from the sides of the angle, converse, then that point is on the angle bisector of the angle. So there's a converse of angle bisector theorem. And you want to write those down. Okay, so we're going to move on to a different picture. We're going to increase the difficulty here a little bit. So take this angle, and what I'm going to do is instead of having just an angle, now I have a triangle. So I have triangle ABC. And we can pretend that this angle ABC was our angle a minute ago. And remember, I bisected it. So what I'm going to do is bisect all of these angles. So here's where all three of the bisectors go. And you could go around and you could indicate that these angles are all congruent to the angle next to them because they've been bisected. Now, what happens here is we've bisected all three of these angles, and if you notice, they intersect in the exact same point. So they all meet right there at point P. That point is called an incenter. The incenter is the intersection of the angle bisectors of a triangle. Now, if you'll remember what we did a minute ago, we said that in an angle, so here's an angle, when there's an angle bisector, the perpendicular distance from any point on the bisector is equidistant to the sides of that angle, but we have to do it perpendicular. So what I'm going to do is I'm going to measure a distance right here. Okay, so there we go. I measured from P over to this BC segment, and I put a Z there. And this angle is a right angle. So I'm going to go ahead and do it over to this side now, from P to AC, because P is also on this angle bisector, so it should be an equal distance from this side and from this side. So I can put the next one on there. So there we go, from P to X is also perpendicular. And then the last one I'll measure down here to BA. So from P to Y, and Y is on segment BA, is also perpendicular. Now hopefully as these were popping up on the screen, you noticed that their measurements were also popping up here. So from P to X, P to Y, and P to Z, they're all 2.65 centimeters. As I change this triangle, no matter how I change it, you notice that the angle bisector is still there. Angle bisector, and they still intersect in the same point, point P, the incenter, and that point is the same distance from each side, measured perpendicularly, all the way around. So no matter how I change this, and I realize you can't change your paper like this, no matter how I change this, that point P stays an equal distance from all three sides. If I start moving these around over here, and you also notice the point P never comes out of the triangle. And you might think, well, it could never come out anyways. What are you talking about? But you'll see with some other things we're going to do, some of these points of intersections like this do come out of the triangles. So what's the point of all this? Why are we doing all this? I want to get rid of the angle bisectors, and I want you to see that in any triangle, when you have the intersection of the angle bisectors, which is what we have there, even though we may not see it all the time, it's there. The point that they intersect in is called the incenter. The incenter is equidistant from the sides. So it's a little backwards of what some people memorize. When you're dealing with angle bisectors, you're concerned about the distance to the sides, not the distance to the angles, which is going to be a different kind of center we learn also. One last thing that's kind of interesting, if I connected this point, and this point, do you see that I could draw a circle through here? You see, I don't know if you can see it or not, but if I did draw a circle through here, what would each one of these pink lines, these equal distances, be called? Okay, that would be the radius. So each of these distances from the incenter to a side of the triangle is a radius of a circle that's inscribed. Okay, so the word is inscribed. So this circle is inscribed in triangle ABC. Now, kind of interesting thing about it is when I move it around, the circle will adjust accordingly, and it will stay inside the triangle. It will never come out of it, and it will always have the center of the circle is the incenter of the triangle. The radius of the circle is the perpendicular distance from the incenter to the sides. So I know that's a lot to take in. We're going to work on it a lot more in class, but I just wanted you to get a good visual aid. If you have any questions about it, you could watch this video again in a couple of days and see if this makes more sense to you.